Hello everyone, welcome to Analog Electronic Circuits, lecture number 8, part number 2. In today's lecture, we will see a new numerical on MOSFET amplifier. So first of all, this configuration over here, DC bias configuration is a drain feedback bias. And overall, it's a common source amplifier employing a N-channel MOSFET enhancement type. So over here, we have been applied a small signal AC via the input coupling capacitor CC1. It reaches the input of the MOSFET amplifier. CC1 value is 0.1 microfarad. RG value is 10 megohm. Drain resistance value is 2 kilo ohm. DC supply VDD is 12 volt. Output coupling capacitor is 0.1 microfarad. The source terminal is connected to the ground. And here we have a load of 100 kilo ohm connected at the output. And output Vout is an amplified AC quantity. So over here, we have been given various MOSFET parameters such as VGS TH, which is equal to 3 volt, VGS on, which is 8 volt, ID on is 6 milliampere, and RAD, small value of RAD is 50 kilo ohm, right? So we can call it as RAD or RO, small RO. So we have to find GM, FL, which is the overall cutoff frequency of the circuit, and the midband voltage gain in dB, right? So let's directly begin our analysis. So in the first part, we have DC analysis. So for DC analysis, frequency is 0. So all the capacitors will be behaving as open circuit because the impedance offered by the capacitance is infinite. So in the circuit, we can see no capacitors present. Now also IG, the gate current in the circuit is 0 because of the presence of the oxide layer in a MOSFET. The input impedance is very, very high. That's why the gate current is negligibly small. So since the gate current is negligibly small, no current, no voltage drop appears across the RG register. Okay. So here we can write no voltage drop across RG. So what does that mean? No voltage drop across RG. That means my gate and the source terminal are at the same potential. Okay, my gate and source terminals are at the same potential. That means we can write over here my VG will be equal to VD. Okay, now let's proceed further. So the drain feedback bias VDS is basically we can write it as drain voltage VD minus VS. Now VS is connected at 0 volt. I mean it's grounded, and drain voltage is given by VDD minus ID RD. Correct? So VDS will be VDD minus IDRD. Now, since we have over here VG is equal to VD, we can say that since source voltage is at ground, we can say VGS is equal to VDS. We can easily make that claim over here, right? So we know what is VDS value. Your VDS value is nothing but VDD minus IDRD. So over here, VGS is also VDD minus IDRD, right? So let's call it equation number 1.1. Next, we assume that the N-channel enhancement MOSFET is in saturation region. Therefore, its drain current can be written as ID is given by ID is equal to Kn times VGS minus VGS TH the whole square. Okay. So the only problem is here Kn value is not known. So how to find the Kn value? So basically these are the parameters given to us. The formula if Kn is not given is as follows. So for finding the value of Kn, this is the formula. So small Kn will be given by basically ID on divided by, okay, sorry for that. ID on, let me just expand it a little more. ID on divided by VGS on minus VGS TH the whole square. So that's the formula. Now you have to substitute the values over here. So that is Kn is equal to, what is ID on? ID on is 6 milliampere. So 6 into 10 raised to minus 3 divided by, we have VGS on as 8 volt. So 8 minus VGS TH is 3. So 8 minus 3 the whole square, that is 5 square. So 6 milliampere divided by 5 square, that is 25. And your answer will be, Kn will be equal to, its value is coming out to be 0.24. 0.24 milliampere per volt square. So that's the value of Kn which we get. Okay, fine. So we have found out the value of Kn. Next, we have to put it in the formula over here and solve it further. So what is ID now given by? We can write that is ID is equal to Kn times. I mean Kn is 0.24 into 10 raised to minus 3 into 10 raised to minus 3 into VGS. VGS TH is 3. So VGS minus 3 the whole square. Okay. So actually we can call this equation as 1.2, not the earlier one. With the values, this equation we can call it as 1.2. So now next what we have to do is, we have to substitute this equation 1.2 in 1.1. Okay. Substitute the above equation 1.2 with 1.1. Basically also we can rewrite 1.1 as follows. So let me just push it forward over here. Yeah. So further we can write it as VDD is given as 12 volt minus ID times RD value is 2000. So I can substitute ID minus 2000. So now what we have to do is, we have to substitute this value of ID from equation number 1.2 in equation number 1.1 over here, and then solve them together. So there are two unknowns, VGS and ID. We have to solve them in the form of quadratic equation. So let's start. So next we have is, put the value of ID in equation 1.1. So we'll put the value of ID in equation 1.1. What do we get? Let's write. So we have, that is VGS is equal to. So let's see what we have over here. VGS is equal to 12 minus ID into 2000. ID is 0.24 into 10 raised to minus 3. So 2000 into 0.24 into 10 raised to minus 3 is basically 2 into 0.24. So that is 0.48, right? So we have over here, we can write this will be 12 minus 0.48 times VGS minus 3 the whole square. So that will be VGS square minus 6 times VGS plus 9. Okay. So we can easily simplify this now. We open the bracket. So we have, that is VGS is equal to 12 minus 0.48 VGS square minus minus plus. So 6 into 0.48 will be 2.88. So 2.88 VGS and minus 9 into 0.48 is 4.32. Okay. So now we can further club the terms together. So which terms we can club together is, we can club this together and this together, and we can club this together, 12 and this together. So we'll take this on the left hand side. So what do we get? 0.48 VGS square, and this one, if we take it left hand side, we get 1 minus 2.88. So minus 1.88 VGS. Okay. And this 12 will go that side, it will become minus 12. This will become plus 4.28. So minus 12 plus 4.28 is 7.68. Okay. And that equal to 0. So solve this in your calculator, put it in the quadratic mode, and you will get two values of VGS. You will definitely get two values of VGS. So we have to write those two values. So after solving quadratically, so we'll write solving quadratically, we get. So what do we get? We get two values of VGS. So VGS is equal to 6.4 volt, or VGS is equal to minus 2.49. So which one to select? We know that VGS has to be greater than VT value, the threshold voltage value. So in this case, since VGS is greater than VTN, the threshold voltage value, in this case it is VGS-TH. So one and the same thing. That's why we will select this value and we will reject this value. Okay. So your VGS is equal to your VGS-Q, we can write it as your VGS-Q is equal to 6.4 volt. Now we know the value of VGS-Q. We can easily find the value of IDQ. So IDQ is equal to Kn times VGS-Q minus VGS-TH, because it is given in this form. So we'll write it as it is. Kn value is 0.24 into 10 raised to minus 3 into VGS value is 6.4 and VGS-TH is 3 volt. So it's basically 0.24 milli into 6.4 minus 3, the whole square. Actually, the whole square is important. Yeah. So now we can calculate this in the calculator. So IDQ is coming out to be 2.77 milliamperes. Okay. So that's the value of IDQ. So we have found out the value of IDQ and VGSQ. Next step is to calculate the value of GM. So let me go slightly up and check it out once. Yeah, this was first step. So next step will be calculation of GM. So let's come over here. We have already have the formula over here. Yeah. So GM will be given by twice Kn VGSQ minus VTHQ. So GM is, that is twice into Kn value is 0.24. So 0.24 into 10 raised to minus 3. VGS is 6.4. 6.4 minus 3. So these are the values. Okay. So it's basically 0.48 milli into 3.4. So that comes out to be 1.623 milliampere per volt. So that's the value of GM which we are getting over here. So that's the value of GM. Okay. Next, our RD value is given as around 50 kilo ohms. So that is given. So that is solved. Now, next we have to calculate AV mid. Okay. So next we have to calculate AV mid. So let's calculate AV mid now. Okay. Let me slightly reduce it a little. Yeah. So first of all, what I will do is I will just draw a small circuit diagram over here so that we can have a reference of what we are doing. So here we have our MOSFET. Let me slightly take it inside. Yeah. Here we have RD. This is RD. Its source terminal is grounded. And here we have a resistor which is connected as a feedback to the drain terminal again. And we have some capacitors over here. This is CC1. We have output capacitor, output coupling capacitor, CC2. And here we have RL and all. This is RL, that's the ground. And here we have V out. This is VDD. This is RD. This is RG. And over here we have our input V in. So now, how to build up the circuit? So first of all, you have to draw the small signal model of the MOSFET. So here we have the gate terminal, the source terminal, and the drain terminal. So first of all, draw the, sorry for that. Draw the small signal model of the MOSFET, that is between gate and source we have VGS, between drain and source we have GM, VGS and RD, correct? So we have drawn this. Next, we should complete the remaining part of the circuit. So let's do that. Let's see that what we have done. So between gate and drain, what do we have? RG. So between gate and drain, we have connected a resistor RG, right? And between drain and ground, we have RD resistance, which is connected to the ground. And also in parallel, we have a resistance RL also connected in the circuit, right? So that's how you transfer the small signal model and integrate into a AC equivalent circuit. So for this circuit, we have to calculate ultimately V out upon V in. So let's just do the analysis without RL. Let's say we will add the RL at the last. Okay. So now let's concentrate. So let's just define the current flowing through RG register as I1, correct? And the current flowing through small RD is V out upon RD, and current flowing through capital RD is V out upon capital RD, correct? So this is my mid frequency small signal equivalent circuit. So ultimately, I have to find out AV mid, which is V out upon V in this case. No longer it is Vs, it is V in this case. Okay. So what do we do first is, first we apply the KCL at the drain node. So what do we get? I1 is equal to GMVGS plus V out upon RAD parallel to RL. So if you see carefully over here, for the from the V out, if you see, RD and small RD and capital RD are in parallel. So therefore, we can write the current flowing through them as V out upon small RD parallel to capital RD. Correct? So here I1 is the incoming current, and GMVGS and the V out upon RD, small RD parallel to capital RD is the outgoing current, are the outgoing currents. So therefore, we have written this I1 is equal to GMVGS plus V out upon RD parallel to small rd parallel to capital RD. Now, from the circuit, we can also write that V in is equal to VGS. It's very straightforward. Their ground terminals are same and their gate terminal is also same. So V in is equal to VGS. So that's not a surprise to write over here. Now, can we write I1 in some other form? Yes. So see, I1 is flowing from the gate terminal and entering the drain terminal. Okay, flowing out of the gate terminal, right, towards the RG resistance. So its value can be written as, I1 can be written as V in minus V out divided by RG. I repeat again, I1 flows out of the gate terminal and enters into the drain terminal. Gate terminal is connected to V in and drain terminal is connected to V out. So we can write over here, I1 is equal to V in minus V out upon RG. Okay, so it's V in minus V out upon RG. So that's what we write over here. I1 is V in minus V out upon RG. So from equation number 2.1, we can replace I1 with V in minus V out upon RG and VGS with V in. Okay, so finally we have everything in terms of V in and V out. So we separate out the terms. We have V in into 1 upon RG minus GM, if you bring this to the left hand side, and is equal to V out into 1 upon RG plus 1 upon small rd capital parallel to capital RD. Now we know that the value of RG is given is very, very large. Okay, it's around greater than 10 mega ohms, around 10 mega ohms. So 1 upon 10 mega ohms is a very, very small quantity. So we can completely ignore 1 upon RG value from here. So we have V in into minus GM is equal to V out into 1 upon RG plus 1 upon RAD parallel to capital RD, right? Now we know that RG, 1 upon RG plus 1 upon small RD parallel to capital RD is nothing but 1 upon RG parallel to RD parallel to capital RD, right? So we can easily write over here, we can, know V out upon V in will be equal to GM times minus GM times RG parallel to RD, small RD parallel to capital RD, right? So this is my V out upon V in formula. And if we put back the RL value, if RL value is present, then the value of AV mid will be given by GM minus GM times RG parallel to small RD parallel to capital RD parallel to RL, right? So that is what we have over here. Fine. So now let us substitute the values over here. So RG value, it's around 10 mega ohm. Let me just elaborate over here. This value is around 10 mega ohm. Small RD value is also large. This value is around 50 kilo ohms. Capital RD value is given as around 12K. So this is 12 kilo ohm. And RL value, how much it is given? Let me check. The value of RL is given as, let me check it once. Okay. The value of RL is given as 100 kilo ohm. Okay. And yeah, let's go back to the calculation of AV mid now. So RL value is given as around 100 kilo ohm. Correct. So if you find out this all the parallel combinations, it will be lower than 12 kilo ohms. Fine. It will be definitely be lower than the 12 kilo ohms. And the GM value we already know how much it is. So finally, AV mid will be if we calculate all the things, it will be minus GM is 1.632 into 10 raised to minus 3 into. So if you solve this carefully, you will get it as close to, I think, RG parallel to RD, parallel to capital RD value is, I will tell you right now, its value is coming out to be how much? 1.9227 kilo ohms. And this is in parallel to RL, that is 100 kilo ohms. So let's do that in the calculator. 1.9227 kilo ohms into 100 kilo ohms will be close to that original value itself, 227K plus 100 kilo ohms. Yeah, its value is coming out to be, this value is, sorry for that. This value is coming out to be how much? 1.886 kilo. So 1.886 into 1.632 milli will be approximately 3.07. Okay, fine. The RD value is not 12. Actually, it is 2. Sorry for that. RD, capital RD value is 2 kilo ohm. Let's check it out if it is 2 kilo ohm. Yes, small RD value is 2 kilo ohm. Okay. So this is 1.9227 parallel to 100K. That is 1.886. So 1.886 kilo ohms into 1.632 milli will be around approximately. So AV mid we are getting around. So let me write it down over here. Let me use a black color. So AV mid is given by minus 3.078. Okay. And if we want to convert into dB, it will be like AV mid will be 20 log to the base 10, 20 log to the base 10 of magnitude of this. It's 3.078. So 20 log, I'm using the calculator, I'm calculating in front of using a calculator. You all are also encouraged to do that. So it's coming out to be 9.76. So this AV mid value is 9.76 dB. So that's the value of AV mid which we are getting. And here we got AV mid in a magnitude form. Okay. So yeah. Let me complete it. Put it inside the box. So we have completed half of the numerical. We have calculated the midband voltage gain. So this AV mid is the midband voltage gain in magnitude as well as in dB. So let's proceed forward and refer to the low and refer to calculate the lower cutoff frequencies. Right now, this was which point? This was, I think, point number 3. Yeah, this will be point number 4. Calculating FL of CC1. Okay. So now I will be putting it back. This is point number 4. I think this is 5, right? Yeah, 4. It is exactly precisely 4. Okay. So we know the difference between your low frequency and the small signal mid frequency equivalent circuit. If you put back the capacitors in a mid frequency equivalent circuit, it becomes a low frequency small signal equivalent circuit. So for FL of CC1, we have to short circuit CC2 and V in. So let's do that. So in the next step, we have short circuited VCC2 and V in voltage, right? So if you observe it over here, if you observe it over here, and this V in is short circuited to evaluate the value of Ri, correct? So now if I observe the circuit like this, I have V in, I have CC1, and I have this system. So for this system, I have to calculate Ri. So I have put entire system inside the box, green color box over here, and impedance seen by this current source will be zero, will be infinite. Sorry, will be infinite. So between the drain and source at this side will be open circuit. Correct. So what is the value of Ri now? Ri will be equal to Rg. Rg is in series. plus Rg plus R small Rd parallel to capital Rd parallel to RL. So RD, small RD, capital RD, and RL are in parallel, and they are in series with small RG value. Okay, so that is how we calculate RI value. Fine. I think next is calculation of R equivalent. So R equivalent and RI will be same over here because we don't have any RC resistance over here. So let's calculate RI. So yeah, do we have the parallel combination of this? So here RD value is how much? RD value parallel to RD is 50K, RL is 100K, and RD value is 2K. So this is coming out to be nearby. RI value will be this entire fraction is coming out. This is RG is 10 mega ohm. So 10 mega ohm plus this entire combination will be lesser than 2 kilo ohms. So that is around 1.923 kilo ohms. So this can be approximated as 10 mega ohms only. Because if you add 1.923 kilo ohms to 10 mega ohms, it will hardly matter. So RI value is coming out to be 10 mega ohms only. Let's consider that. Okay. Next is finding the value of FL of CC1. So FL of CC1 will be given by 1 upon 2 pi R equivalent into CC1. So R equivalent is equal to RI, which is equal to 10 mega ohm. Okay. So let's calculate FL of CC1. So this will be equal to 1 divided by okay, let me just do it again. 1 divided by 2 pi into 10 into 10 is to minus 6, and CC1 value is 0.1 microfarad. Okay, this is plus 6 because it is mega ohm. So plus 6 and minus 6 will get cancelled, and you will have FL of CC1 will be given by, let's solve it in the calculator. It will be 1 divided by 2 pi into 10 into 0.1, and that is coming out to be 0.159 hertz. So that's the value of FL of CC1. That is how FL of CC1 value is 0.159 hertz. Okay, and in order to represent the lower cutoff frequency, it can be represented uniquely like this over here. So between the gain plot and the frequency response, so at 3 dB down, you will get FL of CC1. Fine. So this is what the value of FL of CC1 is. Now next let's calculate FL of CC2. So FL of CC2 is point number 5. So let me change that. Yeah. So FL of CC2 is what do we have to do? We have to short circuit CC1 and V in. Okay. And we put this entire circuit inside the box. So we have over here RL, CC2, and entire system in place. And for this system, we have to calculate RO. So we have put that same thing over here. So this is the green box, and from here we have to find RO. So if you're standing over here, let's look into this box. We have capital RD parallel to small RD, Here we have GM VGS current source will be infinite, it will be open circuit. And then next we have RG also in parallel. If you see carefully the drain terminal over here, we have RG and the gate terminal is connected to the ground. So that means RO is equal to small RD parallel to capital RD parallel to RG. Correct? And I think we have determined this value before. So RO is coming out to be, RO comes out to be 1.9227 kilo ohms. So that's the parallel combination of small RD, capital RD and RG. So now we have to add it to the, we have to add it to the, R equivalent will be RO plus RL, right? So here R equivalent will be, let me add it over here. R equivalent will be, that is, RO is 1.923 kilo ohms plus RL value was given as 100. So plus 100 kilo ohm. Okay. So now that we have to substitute it over here. So we can write over here FL of CC2 will be 1 divided by 2 pi into we have 100 plus 1.923. So 101.923 into 10 raised to 3 and CC2 value is 0.1 microfarad. So this into 0.1 microfarad. Okay. So let's calculate this number and then we will finalize the value of FL of CC2. So FL of CC2 is coming out to be, let's put it inside the calculator, 1 upon 2 pi into 101.923 into 10 raised to 3 into 0.1 into 10 raised to minus 6. Okay. So over here, we are getting the value of FL of CC2. It's coming out to be 15.62. 15.62. Please verify the answer. In your calculators, it might be giving some answer. Please verify it. So FL of CC2 due to coupling capacitor, output coupling capacitor CC2 alone is 15.62. And very clearly, among CC1 and CC2, FL of CC1 and FL of CC2, your FL of CC2 value is much higher. Because I think FL of CC1 was very less. It was 0.159 and here it is 15.62 hertz. So finally, we calculate the lower cutoff frequency maximum of the board and it's coming out to be 15.62 hertz. So that's the lower cutoff frequency of the amplifier. So this is my FL, which is the lower cutoff frequency of the amplifier, of the given amplifier, of the given MOSFET amplifier. Okay, fine. So let's see if anything else they have asked in this numerical. I guess no, I think all the points are cleared, correct? So sometimes they ask to plot the frequency response that can be plotted very, very easily over here. So let me go back to the original numerical. Yeah, so they have asked GM, which we have calculated FL and AV mid. Yeah, so we can easily plot frequency response also. That's very, very easy. Roughly, we can easily plot that. We have done that in the other numericals. So I guess that will be all. We got the value of GM, FL and AV mid for this drain feedback bias common source amplifier employing a MOSFET, right? N-channel MOSFET. So that is all for this session. If you have any doubts, you all can ask.